Hello everyone, my name is Laxmi and I'm a former member of Inclusive Interaction Lab at UC Merced. In this talk, I will present our work on design and evaluation of a silent speech-based selection method for eye gaze pointing. Eye gaze pointing technique uses a webcam to track a person's eyes and determine where they are looking at any given time. The most common application of such a technique is to directly control a mouse cursor using eye movements. While the idea of performing tasks by just looking at the interface is empowering, eye tracking suffers from a Midas touch problem, which is a classic eye tracking problem where the system cannot differentiate between whether users simply scanning the items versus their intention to select them, resulting in unwanted selections wherever the user looks and making the system unusable. One solution to this problem is to use a different action to activate selection. Dwell and speech are the most commonly used hands-free selection method in eye gaze pointing. With dwell, user look at a target for some definite period of time to select it. It is, however, difficult to pick the most effective dwell time since a short time makes a system faster and increases false positive, while longer time makes a system slower and causes users physical and cognitive stress. Speech, on the other hand, is more natural than dwell, but it is unreliable in noisy places, compromises privacy and security, and inaccessible to people with speech disorders. In this work, we studied the feasibility of using silent speech as a hands-free selection method in eye gaze pointing. Silent speech is an image-based language processing method that interprets user lip movements into text. We envision several benefits of using silent speech commands as a selection method. First, silent speech does not rely on acoustic features, thus can be used in noisy places or in places where people do not want to be disturbed. Second, silent speech does not require the use of external hardware, since both eye tracking and silent speech recognition can occur through the same webcam. Third, silent speech is also more inclusive since it can be used by people who cannot vocalize. Towards this, we first propose a stripped-down image-based model that can recognize a small number of silent commands almost as fast as state-of-the-art speech recognition models. We couldn't use existing models because these models are often optimized to recognize phrases, and they are usually trained on large data sets containing around thousands of sentences, resulting in greater variability and ambiguity in lip movements. To disambiguate this, they use multiple language models, which resulted in a longer processing time. In our case, we have a unique situation here, as we are dealing with a small set of words, which is basically a command recognition. So we have used words that can be distinguished based on the mouth aspect ratios to reduce the disambiguation and removed off all language models. This has reduced the computation time substantially. And in order to further reduce the computation time, we applied the concept of keyframes extraction to enable a recognition model to focus on the most distinctive parts of the video sequence and exclude the frames that are not discriminative. So the model works in 3 steps. First, it detects the lip landmarks and then measures the mouth aspect ratio by dividing the distance between the upper and the lower lips with the distance between the left and the right corners of the mouth. All the frames with the aspect ratio greater than 20 are considered as keyframes, and the remaining frames are discarded to reduce the computation time. This threshold was picked based on an ablation study that revealed that a mouth aspect ratio greater than 20 is sufficient to distinguish between the 10 selected commands. Then the extracted keyframes are passed to the recognition module for recognizing keywords. And in this work, we use the state-of-the-art lip type model for recognition. We then conducted a study to compare the performance of the proposed silent speech command model with the state-of-the-art speech and silent speech recognizers to determine if it is reliable enough as a selection method in case-based interfaces. Within the investigated models, we selected the relatively best performed models for speech and silent speech recognition, that is Google speech-to-text and silent command model. Silent command was almost as fast as Google speech-to-text, but was about 24% more error-prone. However, an ablation study showed that the accuracy rate of the proposed model could be improved if we use a smaller set of keywords. The model reached a 100% accuracy rate with just one keyword and close to 95% accuracy rate with 6 keywords, which are acceptable in the context of speech and silent speech input. We then designed a silent speech-based selection method for eye gaze pointing. Towards this, we combined our model with an existing eye tracking model to enable users to point at a target using eye gaze and silently speak the command select to select it. We used Gaze Cloud API in this work for real-time eye tracking using a webcam, since it demonstrated much greater robustness than other APIs. Next, we evaluated our model in a Fitzroy study, which is a well-established method for evaluating target selection on computing systems. It states that the amount of time required for a person to move a cursor to the target area is a function of a distance to the target divided by the size of the target. This law was included in the ISO standard for evaluating non-keyboard input devices by using throughput, which is basically a ratio between index of difficulty and movement time, with index of difficulty being determined by the distance from the target and target width as shown in the following equation. For evaluation, we selected 3 amplitudes and 4 widths based on the minimum and maximum distance possible on the experimental devices, that is 16-inch display in our case. During the study, participants performed point select tasks by pointing at a target using eye gazing and then selecting it using either dual, speech, or silent speech. We compared these selection methods in terms of throughput and error rate. So throughput is again the ratio between the index of difficulty and movement time, as I explained in the previous slide, whereas error rate measures the average percentage of incorrect target selections performed by users in each trial. Results reveal that dual was the best performed selection method in terms of throughput, but was more error-prone as compared to speech and silent speech. On the other hand, speech and silent speech are comparable in throughput, but silent speech is significantly more accurate than the other method. Also, in a subjective feedback, participants were significantly more enthusiastic about using silent speech than the other methods. We then conducted a follow-up study to investigate the most effective screen areas for eye gaze pointing. The purpose was to investigate the optimal screen areas for gaze pointing in order to prevent silent speech performance from being affected by eye tracking. To investigate, the display area was divided into 12 equal parts as shown here. And the study involved participants selecting circular targets using silent speech commands displayed at random locations in different zones. We conducted the study with 12 participants, and results reveal that target selection around the center of the display is significantly faster and more accurate, while around the top corners and the bottom are slower and error-prone. We utilized these findings to inform the design of the final study, where we introduced a new method for menu selection with silent speech and gaze pointing. Finally, we designed an interface for menu selection where we displayed 4 menus, one at a time, categorizing different types of animals, food, popular books, and famous people. We selected these simple categories to assure that the selection tasks do not require specialized knowledge. But considering some participants could be more familiar with the categories than the others, the application also displayed the complete target path on the top left corner of the screen. For each category, there were 5 horizontal menu items, and the vertical submenus under the horizontal menus had either 3, 4, or 7 items. We did not use more than 7 items per submenu to avoid memory overload. And since selecting small targets with eye gaze especially when they are closer together, like in a menu, as shown here, is slow and error-prone. We extended the design by adopting target gravity and 6 silent speech commands to facilitate menu selection. Target gravity uses snap to effect to lock the cursor to the center of the target if the cursor is within 10 pixels of the target, and then remains locked on the target until the gaze path exceeds 10 pixels. We use this behavior to avoid cursor drift during fixation due to involuntary eye movements. And the 10 pixel threshold was used because it felt more natural in multiple lab trials. In addition, we use 2 silent commands to select and close the target and 4 commands for directional movements of the cursor, that is horizontal and vertical direction, which I am going to demonstrate next. Silent speech command right moves the cursor to the right item. Left moves the cursor to the left item. Bottom moves the cursor 1 item below the current item. Top moves the cursor 1 item above the current item. Select selects the current item, and close unlocks the cursor by releasing the target gravity. We then compared menu selection with eye gaze and silent speech with and without silent command. In the command condition, participants used these 6 commands for navigation and selection. Whereas in the without command condition, they used eye gaze exclusively for positioning the cursor and the select command to select the target. During the study, participants performed target selection tasks per menu category using both methods. Results reveal that the method with silent commands was 9% faster and 96% more accurate than without menu commands. And in the subjective feedback, participants found the method with menu commands significantly better in terms of performance, usability, and perceived workload. Now, to summarize the key findings of this work, first, we found that silent speech is a fast and effective alternative to dual and speech-based selection methods in eye gaze pointing, especially when the vocabulary is relatively small. Moreover, it is not best to use dual for the tasks that require using the eyes for extended periods of time, since it tends to affect both user performance, preference, and comfort. Second, when designing eye gaze-based interactive systems, we recommend placing the most important and frequently used interactive elements at the center or around the 2 sides of the display, since top corners and the bottom are usually the slowest and most error-prone. Third, we also recommend using silent speech commands for menu selection with eye gaze pointing, as it is a more private and a secure option and significantly increases users' confidence in selecting the correct option. Besides, vertical and horizontal menus are equally effective in eye gaze pointing with silent speech. Thank you.